Let's consider one more case where the concept of potential energy is often used when applying the energy principle. A potential energy we associate with the force exerted by a spring. Recall that we discussed earlier how to compute the work done by the spring force on an object. We obtained this result. If we take the spring and the mass as our system, then we can define the change in the spring potential energy, delta U sub s, as minus the work done by the spring. Moreover, by expanding out delta U sub s as U sub s final minus U sub s initial and comparing, we see that the spring potential energy can be written as 1/2 k x squared. Let's apply the energy principle to this spring mass system using an energy diagram to help us visualize the situation. First, let's plot U sub s. Here the spatial coordinate along the horizontal axis is x. Note, just to be clear, we define x here as the spring length L minus the relaxed length L naught. So, with this choice of coordinate system and origin, x tells us how much the spring differs from the relaxed length L. X positive means the spring is stretched, and x negative, the spring is compressed. We see that the spring potential energy is positive for both compression and stretching of the spring. Now, if we apply the energy principle to the spring mass system, and we consider the case where there are no energy transfers between the system and the surroundings, then we have delta E, the change in total energy of the system, equal to 0. And that is equal to the change in the total kinetic energy, delta K sub T, plus the change in potential energy of the spring, delta U sub S. Now we can write this equivalently as the total energy E is equal to K sub T plus U sub S, which is constant. Since U is non-negative, the total energy can't be negative. So let's consider the case with E positive, say something like this. We can sketch now what the total kinetic energy must look like. Here it is. What does this all tell us about the motion of the spring mass system? Here's a particular situation for you to consider. Looking at the energy diagram, see if you can answer this question. Let's use the energy diagram to interpret the situation. When we stretch the spring attached to the mass, then in this initial act of stretching the spring, we are, in fact, transferring energy into the spring mass system. We are, in effect, setting the value of the total energy by this action. Once we let go, though, then there are no more energy transfers, and the total energy E will be constant. Now, to represent the total energy for the initial state, we can show this by plotting points for the kinetic energy, the potential energy, and the total energy in the energy diagram. Now, at the instant we release the mass is at rest and the spring is stretched. So here we have initially the total energy E is just equal to the total potential energy. Since the kinetic energy is 0, the system is at rest. Now once we do let go, we know the spring will shorten, pulling the mass towards smaller values of x, which means the potential energy, U sub s, decreases. With the total energy constant, this means the kinetic energy increases, and so the spring mass system has a non-zero total kinetic energy, and therefore a non-zero speed, so it's moving. Now at x equals 0, when the spring is relaxed, the potential energy of the spring has its smallest value, and the kinetic energy has its largest value. The spring mass is moving with its largest speed. But the system doesn't stop there. The spring now compresses, and the kinetic energy decreases as the potential energy increases, and eventually the spring is maximally compressed. The potential energy is once again equal to the total energy. Here again, the total kinetic energy is 0. And the spring mass system is, once again, momentarily at rest. Then, after that, the spring once more starts to extend, the potential energy decreases, the kinetic energy increases. The system comes back to x equals 0, where the spring is relaxed, the kinetic energy is at its maximum, and the potential energy is at its minimum. The spring mass system continues to move in the other direction, and eventually the spring stretches again until the system is back to where it started. And the cycle repeats itself. If we would plot these energies as a function of time, we would see this. The kinetic energy is large when the potential energy is small, and vice versa. This is the correct answer to the clicker question. And this dance between the kinetic and potential energies repeats itself over and over again, all the while the total energy remains constant. Let's back up for a moment here and say a few more words about our choice of system and how that system interacts with the surroundings. First, the system does have multiple parts, the spring and the mass. But for one of the parts, the spring, we consider this to have negligible mass. One of the consequences is that the spring has negligible kinetic energy. So the total system kinetic energy is just the same as the kinetic energy of the object, the mass, attached to the spring. Next, we notice that if we do a careful inventory of interactions, the spring mass system does have interactions with the surroundings. Notice the block is in contact with a surface, and the spring is attached to something like a wall. These are contact forces here. Don't we need to account for these in our energy principle? Well, let's look at the surface contact force acting on the object. If we assume there is no friction, then we know this contact force will just be perpendicular to the object's displacement. So this contact force is non-zero but does no work, and therefore we can neglect this in the energy principle. There are no energy transfers by this contact force. Now, the force that the wall exerts on the spring is also non-zero. It has to be non-zero or we could not compress or stretch the spring. However, at the point of contact where this force is applied, right at the attachment point, there is no displacement, so therefore there is no energy transfer by this force to or from the spring mass system. So even though the spring mass system has non-zero interactions involving these contact forces, these forces don't transfer energy, and so we can apply our energy principle to the spring mass system in the form delta E is equal to 0, or the total energy E is constant. Let's apply these ideas for this quantitative problem involving spring potential energy and the energy principle. Here's a sketch of the situation. First, the initial state looks like this, and the final state looks like this, and we show the corresponding points for the initial and final states qualitatively on an energy diagram. Here's the energy principle, where we see that the initial kinetic energy is 0. The system starts at rest. And the final potential energy is 0. The spring is relaxed. So the unknown final kinetic energy is just equal to the initial spring potential energy, which is the total energy E. We are given enough information to calculate the initial spring potential energy, and so we find the final kinetic energy of the mass to be this. One final note about spring potential energy. You'll recall we wrote down earlier the spring force as a vector quantity in terms of the vector L, which points from the attachment point of the spring to the location where the spring is attached to the mass. The spring potential energy can also be expressed in terms of this vector. Specifically, U sub s is equal to 1/2 times k, the spring constant, times s squared, where s is defined to be the magnitude of the L vector minus the relaxed length of the spring, L0. We will need to use this expression for the spring potential energy soon in an upcoming lab. We will discuss how to do this in detail in a future lecture.